In today's lesson, we're going to try and figure out what is electromagnetic radiation. Is it a particle or is it a wave model? Well, we had the giants of physics, the great gods of physics, Newton and his followers saying it's a particle. But then we had Young and Maxwell saying it's a wave. So what is the particle model? Let's look at this first. What is the particle model? So, the historical particle model describes electromagnetic radiation as a stream of tiny particles radiating outward from a source. A particle is a discrete unit of matter having mass, momentum, which is thus then kinetic energy, and the ability to carry an electric charge. The particle model of EMR is the simplest of all models. It is supported by the facts that EMR propagates in straight lines, can be reflected, and can be absorbed. The pool ball, which was in the picture before, exhibits this particle model. So right here, we have this pool ball which exhibits the particle model. It can be refracted, it can be absorbed. So many things can happen to it. Now, let's take a look at the wave model. And another thing here is to keep in note, a particle, once in motion, can still go through a vacuum and it'll stay in motion. Now let's look at the wave model. The wave model was first proposed by Thomas Young. It is a second model, the wave model, which describes electromagnetic radiation as a stream of transverse waves radiating towards or outward from a source. As you learned in Chapter 8, a wave is a transfer of energy in the form of disturbance. The energy transfer usually occurs in, but is not limited to, a material like medium, such as water. A water wave travels in a straight line, reflects from surfaces, and can be absorbed. For example, water waves, which continuously reflect inside a waterbed, transfer unwanted energy so they can be absorbed by a sponge. So the figure I clicked on to get here is an example. However, this does not require the presence of a medium. Okay, so that's the one thing here. Electromagnetic radiation, we said, does not require the presence of a medium. It's in a vacuum. But yet, according to all wave theories that we had then, most of the time they needed a medium. So here we have water being crashing through. This is the wave theory. It's a medium. Even sound. Sound must travel through a medium. If it's in a vacuum, nothing's heard. So who wins here? Is it the giant Newton? Or is it the tiny Young? Well, you have to understand that this time to argue against the giant Newton was almost scientific suicide. There was one man whose experiment provided conclusive evidence that EMR was perhaps a wave. And this experiment is the Two-Slit Experiment. So, this is what it would look like if it represented a particle. If I shone light through one slit and then through two slits, it would look something like this. That's if it was a particle. Okay? Now, this is what it would look like if it was a wave. Now, how do we know it would look like this if it was a wave? Well, let's take a look at this one here. Let's look at this picture here. And remember when I did that little demonstration in the back with water and I had 2 points tapping against the water and we could see these lines propagating through the waves. Okay? So this is proof that when they did the two-slit experiment, the light showed like this, where we had these nodes. We had antinodes and nodes, which meant electromagnetic radiation is a wave. Light is obviously electromagnetic radiation. Light through the two-slit experiment proved it was a wave. Therefore, electromagnetic radiation is a wave. So there you have it. As of today, there is no scientific evidence, today as in this class, to suggest that electromagnetic radiation is a particle. But there is, however, Young's double-slit experiment to show that electromagnetic radiation is indeed a wave. But later on, in later lessons and videos, you'll see that this plot thickens. things.